All right, gang, from the previous example, I kind of let the cat out of the bag. Not that I would never put a cat in a bag, but figuratively speaking, that there's another way to work confidence center, I'm sorry, hypothesis testing problems. And turns out there is. And we call that the p-value approach. And it has a lot of similarities with the critical value approach, which I've taught you in the previous couple of videos. We start out stating the null and alternative hypotheses, same as before. We state our alpha level and evaluate the sample. We calculate the test statistic. But notice there's no critical value that we calculate. Then we calculate the probability of getting your sample test statistic that you calculated up here, or one more extreme. This is called your p-value. The final step is we make our decision by comparing our p-value to our alpha. If our p-value is less than alpha, we reject the null. The p-value is greater than or equal to alpha, then we fail to reject the null. Now, the only caveat here is when we have, this should be H sub A, that's sloppy there. When H sub A, when the sign is not equal to, so we're conducting a two-tailed test, you must double your probability calculation. Otherwise, you do not double. That probably seems just really, really goofy right now. I think it'll be clear when I work this example. So let's claim, let's say that we have a claim on the table that the population proportion is equal to 20%, and we'd like to test that it's not equal to 20%. We'll assume we're testing at 0.05, and we'll assume that the sample data indicates that 30 out of 115 people, which is about 26.1% or 0.2609, have the characteristic of whatever is being measured in the population. Third thing, calculate the test statistics. So that's going to be p hat, which is our 0.2609, minus our claim of p, divided by the standard error. And when I put that in my calculator, I get 1.6327. Notice this is our test statistic, not our critical value. So we take our test statistic and we record those values on our sampling distribution. Now, the reason we record not only the 1.6327, but also the negative 1.6327 is because we have a two-tailed test. The negative 1.6327 is as equally likely as the 1.6327. Now, to calculate the p-value, we need to get this area. Then we'll double it because this area down here, because the symmetry is going to be the same thing. Circling back, that's why we find our initial probability and then multiply by 2. Finding the initial probability is really easy. Just go to calculator, go to normal. I need area to the right of 1.6327, right? So that's 0.0513. Because I have a two-tailed test, I must multiply by 2. And I get 0.1026. The final step is I compare my p-value to my alpha, which is always stated up here. And what do I get? Well, this is larger, isn't it? So my decision would be fail to reject the null hypothesis. The only decision you can make in test hypothesis testing is either reject the null or fail to reject the null. And we'll learn later that we actually call this statistical significance and non-statistical significance, but we'll cover that in a later video. Now, if I'm going to work this using the shortcut approach, go to stat, go to proportion stats, go to one sample, go to summary. Number of successes here are 30 out of 115. I want P equal to 0.20 and not equal, okay, 0.20. And I don't need a critical value now. And my alpha is 0.05. P-value plot, not really, doesn't do much for us. Calculate, what do I get? Well, I get my sample proportion. I get my 30 out of 115, which is my sample proportion 0.26. That's the value I got right here. Come on over to the standard error. If I worked out this part, that's the standard error. The Z statistic is 1.632. Look familiar? And notice my p-value is 0.1027. Off just a little bit, but only because of rounding. Notice if I hadn't multiplied by the 2, that I would have got the wrong p-value. Anytime I have a two-tailed test, anytime I have not equal to in the alternative hypothesis, I have to multiply by 2 whatever I get as the initial p-value. All right, let's look at another. Let's say we're testing the same thing, that the population proportion is equal to 20%, but now we're testing greater than 20 only. So we have a one-tailed test, alpha 0.05, same sample stuff, and same test statistic. Again, not to be confused with the Z critical value, two different things. But my test statistic and my sampling distribution, the p-value is going to be the area to the right. In fact, all I have to do is just come up here and go edit and just go to the right. My p-value, or I'm sorry, my alpha is still the same, right? Yeah, and compute. Notice nothing changes, right? Standard error. The only thing that changes is the p-value calculation because I don't multiply by 2. Because I'm working with a one-tailed test. Now, how'd they get that 0.0514? Just as you would expect. We need to the right of 1.6327. I don't multiply by 5, or I'm sorry, I don't multiply by 2 because I am conducting a one-tailed test. My p-value is 0.0514. My alpha is 0.05. How does that compare? So again, fail to reject H sub O. Now, let me remove my teaching hat and I'll show you how I would work some problems that you could possibly encounter in research or maybe just an area of interest. Here's the way I would work these problems. Using the results from a recent poll, it was determined that 60%, let me see if I can get that a little bit better, of Americans believe that government regulation on businesses does more harm than good. So we question this claim and would like to test the claim at the 0.05 level. That tells me that the alpha is 0.05. So we select a random sample of 1,762 adults and ask them if they believe the government regulation of businesses does more harm than good. Of the 1,762, 1,004 said yes. What is our decision? Well, first thing I have to think about is what is my known, what's my alternative? So the claim is 60%. So I know that I have these two values. Now I have to look into the problem and see, am I testing higher? Am I testing lower? Am I testing not equal to? When I read this, all I see is I'd like to test the claim. I don't see that I want to test the claim because I think it's higher. Don't see that I'm going to test the claim because I think it's lower. Anytime we see that, we're left with the default, not equal to. Alpha equal 0.05. I really don't even need to calculate the rest of the stuff for this problem. I'm going to go directly to stat crunch, property stat, one sample with summary. Okay. My number of successes are 1,004. My number of observations are 1,762. I'm testing 0.60 versus not equal to 0.60. I don't need critical value. I'll put my level of significance in at 0.05 and hit compute. Now I have tunnel vision on the p-value. Now, even though I have a not equal to sign, I don't need to multiply that p-value by 2. They multiplied the p-value by 2 before they posted it here. So is 0.0097. How does it compare to 0.05? Well, clearly it's less than, isn't it? So I'm going to reject H sub O. That statement is not believable to me based on our sample data. It appears to me that the value for P is not equal to 0.60. Well, if it's not equal to 0.60, we've made a decision on that. It might be interesting to kind of try to determine what it is if it's not 0.60. Let's go to the confidence interval. The confidence interval 0.95. Hit compute. We get 54.7% to 59.3%. So it seems to me that the percentage of people based on this data, and don't go around reporting it because I don't know that it's even current. Represents, well, we don't believe on it. We don't agree on anything anymore. So just about anything that has anything to do with any politics, I expect the values to be about 50%, one way or the other, because we're just so severely drastically divided on things these days. But anyway, it appears that specific to government regulation, that it looks like it's a little bit less than 60%, somewhere between 54.7 and 59.3%. All right. Next study. Results from a recent study indicate that 10% of high school softball players suffer an injury while playing the sport. We question the result and feel that the percentage is less than the indicated. So all right, testing at a 0.01. Let's go do it. So number of successes, we have 1,012 random sample, 83 had an injury. 1,012 is my total. So the hypothesis test should be 0.10. And we want less than 0.10. My alpha value is 0.01. I didn't realize that, but that has to be, we really don't even need the 0.01 there. It's just like a general reminder, and of course it's used to calculate the critical value. But if we're using the p-value approach, we really don't even need that information. So I'm just going to leave that unchecked. We'll make we know what alpha is, and we know that it's not going to be used in the output. It's going to be used right here to make the decision. So I hit compute. My p-value is 0.028. My alpha is 0.01. And it turns out that this is greater than 0.01. So at the 0.01 level, I would have failed to reject H sub O. But kind of interesting, Alpha equal 0.05 is the industry standard. And I'll guarantee you, when you dive into literature and research, you're going to see very, very, very few times that researchers test at a level of anything other than 0.05. So if we tested at 0.05, we reject H sub O, right? But that's not what the problem said. So the way the problem is stated to us, for some reason, they wanted to set a lower level of alpha. They wanted to set it at 0.01 instead of 0.05. That's perfectly okay if it's defensible, if you can defend it. And based on that criteria, based on that standard, our p-value is not less than 0.01, so we fail to reject. All right, gang, that's all I got.